All right, so what we're going to look at now is we're going to look at exact differential equations. A differential equation, m of xy dx plus n of xy dy equals 0, is said to be exact in a region R of the xy plane if there exists a function, call it the potential function, phi of xy, such that d phi dx equals m and d phi dy equals n. So we've got this function phi, and if I take, right, the derivative of phi with respect to x, I'm going to get m, and I'll get the derivative of phi with respect to y, and that's going to give me n. And if that's true, then what I have here is I actually have an exact differential equation. So what we want to do first here is we want to figure out how do we know when something actually happens to be exact. So to prove exactness, what we're going to do is we're going to take something that we got from, say, for example, our Calc 3 when we were doing partial derivatives. So if I look here, I know that m, right, is going to equal d phi dx, and n will equal d phi dy. Okay? And so if you remember in your third semester calculus course, that d phi, if you think about it with partial with respect to x, if you take it with the partial respect to y, it's going to equal d phi of yx. Okay, basically that we can take the partials, if we separate out the partials, one xy, it'll equal d phi to yx. Okay, and so what that essentially means is that if we take my, which is the partial of m with respect to y, if that equals nx, okay, so this is dn dx, and this is dm dy, if those two end up equaling each other, then the differential equation is exact. And we'll see some examples of this in just a little bit. So, actually, let's just take a look at that. So that's the requirement. Pretty straightforward to prove that something's exact. It's just to show that if you take the partial with respect to y of m, if it equals the partial of n with respect to x, then we have something that actually is in fact exact. So now let's talk about the general idea of how we're going to go about solving this. And then we'll take a look at some examples because I think examples are the best way to solve these things. So here's our general thought process. Let's say, for example, I start out with m, because I know m. If I take the integral of m with respect to x, I'm going to get phi. Okay? Because m is the derivative of phi with respect to x, so to take the integral with respect to x of m, I get phi. And then I can take d phi dy, and I'll end up at n, because n is the derivative of phi with respect to y. And then finally, I can go back and take the integral of n dy, okay, and that will take me back to phi. Now you might ask yourself, well, why is it that I actually want to, take this derivative again, d phi dy, to get to n, and then take the integral with respect to n? And the reason why is right here we're going to lose, right, okay, or we lack any functions that are only functions of y. Those got lost when we took the partial with respect to x. So we lack any of those functions that are only functions of y. So consequently, what we're going to need to do is we're going to take that derivative, and then at the end stage, right, when we take that derivative with respect to y, we're going to make a comparison. We're going to compare, okay, d phi dy that we got from our earlier one, okay, to n. We'll make a comparison between those two. Once we do that, that's going to give us actually all of our functions of y. And so then we can take the integral with respect to y, and we end up back at phi. Now we can actually do something similar. We can actually do something similar if we were to start at n. If we started at n, right, we'd actually go through and we'd take the integral of n with respect to y. That'll take me to phi. And then here, though, we will lack functions of x only. Because what n was it was the derivative with respect to y. Then we're going to take d phi dx, and that's going to take me to m. At m, we'll make a comparison. We'll compare d phi dx to m. So we'll compare d phi dx to m at that point, and then we'll integrate m with respect to x and end up at phi again. Okay? So basically, we're using that fundamental theorem of calculus in order for us to add in all the information that we need in order to fill out our entire exact differential equation. So that's the thought process that we're going to use in order to solve exact differential equations. So let's take a look at an example, and I think an example will show us how exactly this process works. Okay, you just want to remember what m is. M is the derivative of phi with respect to x, and what n is the derivative of y with respect, or the derivative of phi with respect to y. So we'll start out by proving exactness. Since this is the function with respect to dx, we'll write it as sine of xy plus xy cosine xy plus 2x, that's equal to m. And so n will equal x squared cosine xy plus 2y. Now what we want to do is we want to find my. So my, this first one, sine of xy, is going to end up giving me x cosine xy plus, we'll get x cosine xy plus xy times x sine, and actually this will end up being a negative, so minus xy times x sine xy. This whole thing ends up equaling 2x cosine xy minus x squared y sine xy. And x is going to then be, we'll take the derivative with respect to x, this top one, so this is going to be 2x cosine xy minus x squared sine, or x squared y, because we'll take the derivative of xy, so x squared y sine xy. And the 2y goes away because it has no x's in it. So if we notice here, what we're going to notice is we're going to notice that these two, they in fact are the same. So my equals nx. So the dE is exact. So we've actually now proved exactness. So now let's solve this exact differential equation. I'm going to actually start out here with n. And I'm going to start with n because I believe n is easier to differentiate, to take the integral of. So I take the integral of x squared cosine xy plus 2y dy, and that's going to end up equaling, okay, x squared divided by x sine xy plus y squared plus some function of x, an unknown function of x. So this is going to end up equaling x sine xy plus y squared plus h of x. Now what I'm going to do now is I'm going to take d phi dx. So I'm going to take the derivative with respect to x. So that's going to equal sine xy plus xy cosine xy plus h prime of x. Okay, so the derivative of this piece right here, and then the y squared goes away because obviously we're taking the derivative with respect to x. It ends up being a 0. Okay, now what I want to do here is I now need to compare to m. So m is this piece right here, so it's going to be sine xy plus xy cosine xy plus 2x equals sine x y, xy plus xy cosine xy plus h prime of x. So h prime of x, what we'll see is these guys go away, this goes away, right? We end up with h prime of x equals 2x. So now all I need to get back, if you notice, we have phi. Phi is this thing right here. This is phi. Okay, all we're missing is h of x. So I take the integral of h prime of x dx, that'll equal the integral of 2x dx, and that'll end up equaling x squared. So now all I need to do is to plug that in. So phi will end up equaling x sine xy plus y squared plus x squared. And that's what phi is. Phi is that potential equation. To finish this out, the actual solution will set phi equal to a constant. Because if you remember, we had phi equal to, or we had the derivative of phi equal to 0, okay? And so what that meant was, that we will end up having a constant on the other side. So the actual solution is x sine xy plus y squared plus x squared equals some constant c. And that's the solution to our differential equation. So if you think about it, it's pretty straightforward. Okay, what you do, you're going to start out with your original exact equation. We've proven that it's exact. We start out with one or the other of them. So in this case, we start out with n. We took the integral with respect to its particular derivative. So in this case, dy. Okay, and we end up with phi, but we're missing the function of the other variable. Okay, we're missing the part of the function that is just the other variable. So we'll take the derivative. Once we take the derivative, we're going to compare it to either m or n, depending upon which one we're looking at, which one we started with. And once we've figured out what h prime of x is, or h prime of y is, we're going to actually take the integral of that. That's going to fill out the last part of our exact differential equation. That's going to give us phi. Okay? Once we get phi, all we've got to do is we've just got to set that equal to some constant c, and that, in fact, is the general solution. There's our general solution. Let's take a look at another example so we can see actually how this is done and just kind of like solidify what's happening. So let's look at find the general solution of y over x dx plus 1 plus natural log of xy dy equal to 0. So what we'll first do is we'll prove exactness. We'll show exactness. Okay, and so my is going to end up equaling 1 over x. Okay, and nx is going to end up equaling the derivative of xy with respect to x, so y over xy, which ends up equaling 1 over x. So 1 over x equals 1 over x. Check the two equations. The equation is exact. So that equation is exact. So now what I want to do is I want to go in and I'm now going to utilize my method. If I look here, probably y over x is the easier of the two to actually take the integral of. So I'm going to take the integral of y over x dx, and this is actually just equal to the integral of y times 1 over x dx, which is equal to y natural log of y. Okay, plus some function h of x. Okay, we don't know what natural log of x, not natural log of y. Y natural log of x plus h of x, or h of y. H of y. Since we took the integral with respect to x, we're going to recover an h of y. So now what I'm going to do is I'm going to take the derivative. I want to find d phi dx. D phi dy now, pardon me, right? We took the integral with respect to x, now we're going to take the derivative with respect to y. This is going to end up equaling, okay, the natural log of x plus h prime of y. Okay? Now that we have that, natural log of x plus h prime of y, what we need to do is we in fact need to go in and we need to set that equal to n, right? So now we're going to set equal to n. So this is now going to be 1 plus the natural log of xy equals the natural log of x plus h prime of y. Now, unlike the last one, we don't get something that's quite as neat and tidy as we had before, but this is certainly actually doable. This could be 1 plus the natural log of xy minus the natural log of x equals h prime of y. And if I rewrite that, that's going to end up giving me 1 plus the natural log of xy over x, which is just 1 plus the natural log of y, which equals h prime of y. Now, we just need to integrate that one. We're going to integrate h prime of y with respect to y. So h prime of y dy is going to end up equaling the integral of 1 plus the natural log of y dy. Okay? And we actually utilize integration by parts in order to do this one. Okay? And what we're left with, after we use integration by parts, is we're going to be left with y natural log of y. Okay? And that's it. So, we'll take this piece, our h of y, this is h of y now, okay, plus y ln of x, and that's going to give me phi now. So phi is going to equal y natural log of x, okay, plus y natural log of y, and that's phi. And so my general solution is now, it's not just phi, my general solution is y ln of x plus y ln of y equals c. And that's how it's done. In this case, we started out with m. We took the integral of m with respect to x, and we got some function, right? We got phi, but we were missing the function with respect to y part. So we take the derivative with respect to y. We end up with natural log of x plus h prime of y, okay? And then, given that that's the case, we could just make a comparison to n in this case now. So we compare to n, do a little bit of algebra magic, okay, to get 1 plus natural log of y equals h prime of y. And then we'll take the integral with respect to y to get hy back. So now, what we're going to do is we're going to take, okay, we'll now have, this here is phi. Okay, don't forget that this top one, the first integral that we took was phi. And now we actually have the second piece of phi right here that we can add to it. Once we found what phi is, we set that equal to some constant, and that gives me my general solution.